How do you write good code? A question which is both stunning in its simplicity and breathtaking in its reach. In some sense, it is this question that preoccupies each and every day of our professional lives. But while the particularities of how we write good code may vary between domains, there is an overarching principle which unites them. Overwhelmingly, we write good code by splitting it up. But this answer isn't totalizing because it just raises another question. If we write good code by splitting it up, what is the mechanism by which we split code up? Once again, this question has an overarching answer which reaches every area of software engineering. Overwhelmingly, we split code up by calling a function. But we're not done with answers begetting further questions just yet, because this answer leads us to ask, how exactly do we call a function? And this may seem like a ridiculous question with an obvious answer because, of course, we call a function foo with a parameter x by writing foo of x. But this is a notational or syntactic answer. It just tells us how we communicate our intention to call a function to the compiler. It doesn't give us any information of what actually constitutes a function call. And so if we think about this for a while, we can arrive at the following set of steps which constitute a function call. First, in order to write foo of x, we need to come up with an x, and so we need to prepare or synthesize some arguments. Thereafter, those arguments need to be brought into the context in which the function will run. A stack frame needs to be allocated, therefore. We can detect this moment in our program's execution as when copy and move constructors for arguments run. With this in place, we then surrender the CPU to the function for it to make use of to make forward progress. And as it reaches its end, it communicates its returned value to us. The stack frame is cleaned up and the function call completes. But we held up a function call as the mechanism by which we split code up, and now we have identified 4 distinct phases which in turn make up a function call. So what if I want to make this reflexive? What if I want to split up the function call protocol itself? And at first glance, it appears there's hope. It appears this is going to be easy because we already have a solution for how to separate out preparation and synthesis of arguments. We already know about function currying, which we can use to accept the function, partially apply it, and generate an entirely new function, which can be used with the process of selecting those arguments abstracted away from us. But as we move later into the function call protocol, as we move to those last 3 steps, we run into a problem. If we prepare a stack frame, the stack is now carefully prepared for another function to run and not us, which drags us inexorably into the remainder of the protocol as we surrender the CPU for use by the function to make forward progress, which it has at the exclusion of us. It is making forward progress, and so we can't, and we are drawn further and inexorably through the protocol until we get to the point of return. A point of return which returns to the exact point in the source code from which we called the function. And so these things aren't just coupled morally, they're also coupled lexically. But what if I want to try anyway? What if I want to bootstrap the function call protocol from nothing? Of course, in this new ecosystem I'm synthesizing, I want to preserve the abilities that regular function calls already have. And so I want to have some way to represent the arguments separate from invocation to preserve that quality of the ability to curry functions. Then we need to move on to the other components that regular function calls don't have a solution for. We need some way to abstract away the return path by adding to our ecosystem a completion or a continuation or a callback, which receives the synthesized values and acts upon them separately from the point of call. But these 2 things are useless independently. We need some way to bring them together, a process which unites them. But if we think back to our regular synchronous function call, we need something else, because we prepared a stack frame for that function to use for local storage. And so it's not sufficient to, yes, unite these 2 entities. They also need to produce a context in which the function can run, some private storage it can use to accomplish its goals. And this diagram might serve to decompose the problem conceptually, but the diagram doesn't establish a vocabulary that we can use to discuss our new ecosystem and explore its consequences. For that, I need to give each member of this ecosystem a name, and so I will first look to that pack of arguments and decide that I'm going to call that a sender. I'm going to look to the completion or continuation or callback and name that a receiver. The context that is output by bringing these two together, I will call an operation state, and the operation that unites them, I will call connect. But this diagram just shows where data is resident in the ecosystem, and in some sense, data flow is the least important part of a function call. Functions are about execution, not necessarily about data, and so far we don't see how we can delegate the CPU to this decomposed function to give it permission to make forward progress. And so we need to turn to the operation state and decide that now it gains an operation called start, which gives this decomposed function the right to start making forward progress. And with this decomposition, we can immediately turn our attention to some code. We can look at some regular old-fashioned synchronous code, which has an optional and has a very simple function which simply returns 5. Then we perform a regular function call invocation and use the value returned therefrom to populate and engage the optional. No one in this room has any difficulty understanding this code, I'm sure. But what if we want to apply our shattered, decomposed function call protocol to this example? What if we want to rewrite it, splitting things out at every level of analysis? We instead write something that looks like this. We still start with an optional, but now in our new ecosystem, we have to fully curry functions in order to call them. We have to form a sender which fully embodies the latent execution. And so we call std execution just and pass it 5, and in so doing we get a sender which represents a fully curried version of a function which, when invoked, simply returns 5. This is identical to what we had on the preceding slide. But we need to figure out what this function should do when it eventually returns, and so we need to author a receiver. The receiver has a nested type alias which simply identifies it to the concepts machinery of std execution as a receiver, but more interestingly, it has a set value unary invocable member function. This is the member function to which the returned value of the associated asynchronous function is returned. It encapsulates the continuation action that is performed thereupon to effect the remainder of the computation. But in our case, the remainder of the computation is just assigning that integer through to the optional, exactly like the synchronous example did. But as I reviewed earlier, this does us no good unless we bring those two entities together, and so we connect the sender and receiver to obtain an operation state. This is like obtaining a stack frame in the synchronous domain, except now we have control over this as a variable. We're not committed to immediately begin execution. We can just leave it over in the corner until we decide we actually want to make forward progress. But in our example, of course, we want to immediately make forward progress, and so we immediately call start and allow the latent execution represented by the operation state to actually begin. It is only on this line of code that we go out to the sender, which is now connected to the receiver, obtain that value 5, pass it through to set value, and assign it into the optional. And this example is illustrative, but it doesn't really identify the finer points of how entities in this ecosystem interact. For that, we need to understand the ground rules that std execution obeys, the ground rules that are obeyed by senders and receivers. And this is communicated through something called the receiver contract, which controls the interaction between operation states, which represent operations, and the receivers they contain, which determine what happens when that computation completes. As we saw on the preceding slide, it's perfectly plausible that you connect a sender and receiver and obtain an operation state, but then neglect to start it. This would be like never calling a synchronous function. We would be utterly astonished if a function that we never called returned. How would that even be represented in code? And therefore, when you create an operation state by uniting a sender and receiver but neglect to start it, you are guaranteed that no completion signal will ever be sent to the receiver. After all, as we just established, functions that are never called don't return. On the other hand, if you do call start on that operation state, the contract now comes into effect and binds both you and the function that you called. You are now bound to keep that operation state within its lifetime until you receive a completion signal. The operation we saw on the last slide completed synchronously inside of start, so this wasn't much of a requirement, but there are much more interesting operations we're going to get to authoring that do not complete synchronously inside of start, and in those cases, you are bound to keep the operation state within its lifetime until it completes. This might sound terrifying, but as we're going to iteratively see over the next 2 hours, this is actually easy when we use the senders and receivers ecosystem. In exchange for upholding this side of the bargain, you receive a guarantee from the ecosystem that your receiver will receive exactly one completion signal. Start will not throw any exceptions. You will not receive 2 completion signals. You will receive exactly one completion signal in the same way that regular synchronous functions return control to you exactly one time. But in explaining this slide, I said completion signal and not set value, which evokes to us the idea that completion signal is a category which has members other than set value. And so we should explore what those other members are as we continue to probe the ecosystem we're exploring. Let's take a look at a slightly more complicated piece of synchronous code. We still have that function that just returns 5, but now we have a higher order function which accepts it, invokes it, and layers some filtering on top of it. If the predicate it embodies is not satisfied, it throws an exception, and indeed we can see that's the case based on the comment at the bottom of the slide. Once again, this is not particularly interesting code. What is more interesting is its isomorphic code in senders and receivers. Since we have 2 outcomes now, we now see that we have an optional of a variant representing the 2 outcomes. We still have a sender, which is a just sender having accepted 5, but now we have this adapter, which is obtained by calling stood execution then. And the name of that function evokes to us the idea that this might be a continuation which takes place after some predecessor action. And this is borne out as we look at the lambda that is passed, which embodies the exact filtering we saw in the synchronous domain. Curiously, however, the code in the red box doesn't actually contain that predecessor. It's just the moral concept of a continuation bereft of the predecessor. It succeeds. Moving our eyes down the slides, we see that we have added set error to the receiver so that we can receive value sent in the error channel. As I said before, start can't throw exceptions. Once you are inside the senders and receivers ecosystem, it is totalizing, and the only way out is down into the receiver, fulfilling the receiver contract. Therefore, when the lambda passed to then throws an exception, the machinery which implements then is obligated to catch it and send that exception down into the receiver. In the same way that when an exception is thrown, it is emitted from your function, not for some randomly chosen other function in the program. Then as we look down to connect, we see that rather than just passing in the sender, we use the pipe operator to compose our sender and the adapter. We don't just generate the value 5, we also attach a then continuation to perform some action after 5 is returned before control goes through to the receiver. But these are not the only curious things about this example. The actual synchronous code that we're operating in terms of is also curious, because it uses a higher order function to accomplish something utterly banal. I would be astonished to see the modal C++ developer write this code in this way. I would expect them to instead write this. And yet, as we explored the asynchronous domain in response to this example, we didn't find any mismatch. And the reason for that is because of the full currying of the senders and receivers ecosystem and the call graphs that naturally result from it. On the left, you can see the call graph of the synchronous code we wrote originally and the asynchronous code. Because it is higher order, we can see that F2 is the one that actually calls F1 rather than main calling both of them. We have this linear call graph. On the right, we see the call graph that we would expect in the synchronous domain, that we would expect to be casually written by your modal C++ developer. Main first calls F1 and then calls F2. But as we think about this execution, it would require something. It would require late binding of parameters. We wouldn't be able to synthesize a sender for F2 until we have the value that F1 returns. We would need to delay currying those arguments and generating the sender. And as we think back to the asynchronous example, there wasn't any opportunity to do that. Once we had selected the asynchronous code we were going to execute, there was no seam to change the parameters that had been passed to senders. No, that must be a new addition to the senders and receivers ecosystem that we haven't yet considered. which allows us to late bind senders as an analog to the fact that synchronous code is exceptionally good at letting you delay selection of parameters. The primitive that does this is std execution let value. It's like std execution then in that it pulls you out of the asynchronous domain into asynchronous invocable, but instead of it just filtering values traveling down the value channel, it actually allows you to parameterize a sender lazily and then invoke it in line. We can actually see the expected C++ example written in terms of let value, and forgive me for the fact that it's complicated, the std execution framework doesn't really lend itself to parsimonious late currying. We have just piped into let value this time, and inside of let value, we're not trying to synthesize a replacement to go down the value channel. We're trying to synthesize a new sender which will be returned, a new asynchronous function which will be invoked in response to the completion of the predecessor. Unfortunately, as I pointed out earlier, this just leads to code duplication because of the structure of std execution. In reality, the best way to write this code in std execution is by using then and not let value. But given the richness of this new ecosystem, we need to stop just figuring out how we can do the same things in the asynchronous domain we do in the synchronous domain. After all, the reason we go to the asynchronous domain is to get power and expressiveness that we don't have in the synchronous domain. And one of those examples goes like this. In the synchronous domain, you call a function, and as I mentioned earlier, that function steals the CPU from you. You can't perform any computations while it's running. You can't realize that, for example, something may have happened which makes that function call obsolete. You're obligated to let it run to completion, and when it returns, only then do you realize that you don't need that expensive to synthesize result. In the asynchronous domain, on the other hand, you may start an operation and then get control of the CPU back. You may run some subsequent operations and then realize that you don't actually need the value of that computation at all. You now have full control of the CPU, so you can perhaps move on with your life without completing that computation. But as we reviewed, the receiver contract bans the most obvious way to do this. We can't just destroy the operation state and hope that ends the operation, because the receiver contract bans that. We need some way to ask that operation to please stop making forward progress and satisfy its receiver contract as soon as possible. What we're discovering is the final completion signal in the std execution set of completion signals. And that is set stopped, which is sent in response to a stop request to signal that the operation simply stopped trying to make forward progress. This isn't an error. After all, nothing went wrong. But it's not a value either, because it doesn't indicate that the function completed, it just indicates that it gave up trying. But how exactly do we ask something to stop? We would hope that our generic ecosystem has some generic way we can interact with asynchronous functions to request they perform this action, and indeed it does. We just haven't explored the ecosystem thoroughly enough to find that seam yet. We're well aware of senders and receivers and operation states, but what we don't know just yet is that every receiver has an associated environment, a collection of queries that can be performed to get information about which the environment in which the receiver is running. Every environment can be queried as to its stop token, and a stop token provides a channel through which stop requests can flow. If the operation respects the stop token, it can wait for those requests and stop in response thereto. But that, of course, raises the question of where did the stop requests come from if the stop token is just a mechanism for delivering them? And the answer to that is that stop tokens come from a stop source through which stop requests can be submitted. And this is not new or novel information. This is not something brought to us by std execution. The C++ standard library has had stop tokens and stop sources since std jthread was added. But std stop source and std stop token are particular concrete types. They have a particular concrete set of design decisions that were made to synthesize them. They may not be suitable for every domain. And so, true to the fact that it's a generic framework, std execution lifts the idea of std stop token to the conceptual domain. It provides us with the concept std stoppable token, which just embodies the requirements a stop token must obey. You can now provide a stop token with any set of design decisions you want, provided it gives the appropriate API to communicate stop requests through to your operation. And this actually completes an overview of the senders and receivers ecosystem. We've now reviewed everything that contributes to that generic ecosystem. But I doubt that review is very satisfying. You probably have some burning questions. You're probably wondering, how exactly can I take advantage of all the cores in my big server with all this conceptual overview? And the answer to this question is incredibly dissatisfying, because the answer to this question is that parallelism is orthogonal to asynchrony, which means that std execution is concerned only with concurrency, with dividing operations into small parts that can be scheduled independently. It says nothing about whether any of those parts actually run in parallel. But in answering that question, I said a key word. I triggered us to ask a follow-up question. If std execution isn't bringing me any parallelism native to its model, but it is bringing me concurrency, where is the concurrency? Because we saw operations that complete synchronously inside of start and give us no concurrency whatsoever, but we didn't see anything that actually causes operations to go off and run in the background. And the answer to this that std execution provides is equally dissatisfying. Because the answer that std execution brings us is, well, you just need to bring your own. And the reason it provides this answer is because std execution isn't trying to actually bring us any of those basis operations. It's just a framework. It's just trying to provide a lingua franca for us to communicate about asynchronous execution. It's trying to bring us that decomposed function call, and then we can implement whatever we want with it. But this is a little bit of a cop-out. Without a guide, how are we supposed to figure out exactly how to piece those things together to form the large, high-level systems that we want to actually build? Sure, we can call just and then and move some integers around, but that's not really an interesting solution to any problem that anyone is encountering in the real world, is it? And so I want to revisit a talk I gave in 2021. A talk where I gave the overview of the architecture for an asynchronous networking server. I want to take and re-implement that asynchronous networking server from the bottom up using only std execution to show how primitives can be bootstrapped and combined to form a real-world solution to a real problem. And the fact that we're writing a network server might evoke the idea that maybe we're going to speak some protocol. And indeed, this is true. This server is going to speak this proprietary protocol, which is in use inside of my company. And so we might imagine that the first thing we want is the ability to asynchronously speak this protocol. We want to read and write exactly one message asynchronously, for example. But we started out this talk by saying that the way we write good code is splitting it up. And these aren't really indivisible logical units at all. Instead, maybe we want a way to perform lower-level buffer I/O, reading and writing one buffer at a time asynchronously. But anyone who's ever actually performed low-level I/O knows that these are not indivisible primitives, because the operating system doesn't give you read and write one buffer functionality. It gives you try to read and write one buffer, and I'll tell you how many actually succeeded. And so these are composed out of an even lower-level primitive, which is just reading and writing some bytes. But we want to write asynchronous code. We want to write code that completes asynchronously, not synchronous code that just reads and writes bytes. So what we actually need is some I/O multiplexing system. And if you've been around in the asynchronous world for a while, you'll know there are people out there working on implementations of I/O multiplexers built on top of IOU ring using std execution. And that might seem like a great place for us to start, and I certainly thought so until I logged into the development server at work and asked it, hey, development server, what kernel version do you run? And it said IDK, one that's too old for IOU ring. And so instead, I need to go off and use epoll. And this may just seem like me belly aching about a tragedy that I encountered to you, but this is actually a boon. I didn't go off and write this epoll context and then come here to stand before you and say, I wrote an epoll context, we're going to use it. No. Instead, we're going to walk through every single line of code that is required to build this epoll context and bootstrap the guarantees of std execution on top of it. So let's do a brief review of one of Linux's API. The first function we're going to encounter in interacting with epoll is, of course, a function which creates an epoll file descriptor accepting a size. That size is obsolescent on new kernels, and so I'm just going to opaquely pass one into it for the remainder of this talk. Since this is an I/O multiplexing utility which deals with many file descriptors, we want some opaque closure data we can associate with each of them so we can quickly resume tasks when we get readiness notifications. So we have this union of many members, but the only one we really care about is the void pointer, and so I took all the other ones off the slide. Just having closure data doesn't really do us any good if we can't associate it with a set of bits of readiness that we want to wait for, and so we have an epoll event structure that does that. Epoll is a readiness-based API, and so we fill in events with bit masks corresponding to the kind of readiness we're waiting for, readability or writability. And then we have a closure associated with it. Of course, these do us no good if, in turn, we can't actually use them to talk to epoll, and so we have a function, epoll.ctl, that allows us to express interest in a file descriptor. We pass it the epoll file descriptor, whether we're adding, modifying, or deleting, and then we pass it the target file descriptor and the event object we want associated with it. This allows us to set up asynchronous computation, but does absolutely nothing to make any forward progress on anything. For that, we need epoll wait. When we call epoll wait, we give it an epoll file descriptor, a buffer of events, and a timeout. Of course, for the remainder of this talk, we're just going to pass -1 as the timeout because we want to wait forever. From these low-level C primitives, we're going to build this beautiful senders and receivers-based API, this beautiful epoll context. The two last member functions are the most interesting parts of this API. When you call wait, you give it a raw file descriptor and a raw bitmask, and it returns to you a sender which, when connected and started, is going to wait for any of those readiness through epoll. Note that this is latent execution. It just goes up and sets things up. It doesn't actually make any forward progress. In order to make forward progress, as we reviewed on the preceding slide, someone needs to call epoll wait, and that's going to be whoever calls the run function. They're surrendering their thread to call epoll wait in a loop and drive all the receiver contracts through to satisfaction. This is a very important part of this API. If you don't call run, you don't make forward progress. If you don't make forward progress, you don't satisfy receiver contracts. If you don't satisfy receiver contracts, you broke the model. And so if you call wait and get back a sender, connect and start it, you had better come back and call run, otherwise your program is not going to behave in a sane way. But don't worry, this seemingly sharp edge is going to be neatly abstracted away on perhaps the fifth to last slide of this entire talk. Moving on from this, we can start actually writing the code as we were promised. We can start working on the constructor, which of course calls epoll create with that opaque value of 1, which I mentioned earlier, handles errors, and returns from our immediately invoked lambda expression. What it's constructing is a safe file descriptor, as you can see on the bottom of the slide. I used NVIDIA's implementation of std execution in preparing this slide, and it comes with extensions in the exec namespace, and we're going to see those from time to time throughout the remainder of this talk. I just grabbed this one because it kept me from having to write my own RAI wrapper for file handles. But that's not really the most interesting thing on this slide. What's more interesting is how terse that C error handling is. What's more interesting is the fact that I'm throwing a system error which isn't a std system error, and I'm passing it a string and not an error code. What this system error does internally is it goes off and grabs erno and composes a nice descriptive string that can be shown to my users in response to the failure. Instead of getting something opaque like too many open files, which tells no one anything except they need to go yell at their nearest developer, they instead get an error message like this, which may still trigger the same response, but at least that developer can have some idea where the failure actually came from. All that time and attention spent talking about the receiver contract leads us to think that maybe we need some way of keeping track of operations. Since we need to drive them all through to completion, we need some way to perhaps enumerate and store them, and so that might lead you to believe that inside the epoll context we have something like a std list of operation states. Because operation states are immovable, we would of course reach for a container which can accommodate such types. But there's two problems with this formulation. The first problem with this formulation is that in that tweet I showed you a few slides ago, you were promised a zero allocating async system. And now I'm reaching for std list, which definitely allocates. The second and more serious problem is this diagram belies the structure of the senders and receivers ecosystem. We don't get to pick where operation states live. That's up to the person who called connect. And in fact, this property of senders and receivers, that the operation state's lifetime is managed by the person who calls connect, is one of the powerful elements of the structured concurrency it brings us. And so I can leverage that. I can take advantage of structured concurrency for the first time in this talk directly and flip this model on its head to do bookkeeping about our outstanding operations. Instead of allocating some node and putting the operation state inside of it, I can rest assured knowing that our user is going to obey the receiver contract as well. I can just flip this on its head and use an intrusive linked list and make that node part of the operation state that I give back to my users. Now they need to deal with managing that memory, not me. I don't have to allocate anything, and we get to take advantage of structured concurrency. Of course, the problem with this is that it means I have to write a bunch of boilerplate to actually create an intrusive linked list. I create a tag to uniquely identify this list. I create a hook, which we're going to derive from, which actually puts that node inside our object. And then I have a base, which is the base class for my operation states, which derives therefrom. Then I have to go and do a bunch of magic with boost intrusive to make it summon a linked list appropriately parameterized, and then I put it in as a member. Which brings us to looking at that base class. Because we don't know the exact types of receivers our users are going to use, because they get to pick any one they like, we need a layer of type erasure between us and the receiver. We need to type erase the transmission of completion signals there too. Because our user can provide any type, we need to give ourselves this consistent interface. Note also that, once again, I've copied over the fact that we're derived from the waiting hook, so even though you can't see it on the slide, rest assured the pointers necessary for that linked list are resident herein. Which brings us to the other side of type erasure, the derived class where we actually receive the receiver as a template parameter. We stamp out the needed members, a reference back to our epoll context, the events we're going to wait for, and of course the receiver, and then we can move on to stamp out some boilerplate. Just like with receivers, operation states need to opt into being operation states by having this nested type alias to communicate with the concepts machinery in std execution. And of course, it's not much good to have an operation state if you can't construct one, and so I give it a perfunctory constructor. Then we need to turn our attention to actually type erasing the receiver, to actually passing through the impulses we're going to receive from the context. And so I override both of those functions and simply pass through by invoking the appropriate customization point object from std execution. But notice something interesting here. I move the receiver into both of these customization point objects. This is me expressing in code that the invocation of these customization point objects is consumptive. It's consumptive because of the receiver contract. I can only send one of these completion signals to a receiver, and so while I send one, I'm done with the receiver, which necessitates me using std move to express that. Which brings me to the user-facing surface of the operation state, the point where the user says that the execution I represent should transition from latent to active, the implementation of the start member function. The first thing I need is an epoll event which represents the readiness that I'm waiting for. And so I zero initialize one and fill in the events, but curiously, I OR in this epoll one-shot. The reason that I do this is also related to the receiver contract, as are so many things we're going to encounter as we continue to explore std execution. If I don't provide this, epoll will continually notify me of readiness. It will wake up over and over and over again and tell me as long as a file descriptor is readable or writable. But if it does that, we may end up sending multiple completion signals through to the receiver, which is in violation of the receiver contract. I could, of course, when I wake up, go and use epoll CTL with epoll CTL del to remove the association, but that would constitute an additional unnecessary system call. The kernel supports doing this natively, and so I simply combine events with epoll one-shot to opt into this behavior. I assign through the closure pointer, and we can move on. We can move on to some implementation detail lambdas that are going to make a subsequent slide much simpler to implement. The first, which is called fail, wraps up the act of failing because one of the system calls we tried to perform didn't succeed. Remember, we can't throw from start. We're now inside the asynchronous ecosystem of std execution. The only way out is down into the receiver. And so we synthesize an appropriate system error, catch it, and push it down the error channel. Note that this construct may seem unusual to people who are used to using something like std make exception putter, but if you think about the interface of std make exception putter, it actually accepts the exception type. The exception type is system error, and system error is constructed from a string, and so constructing it could throw, and so std make exception putter could throw, and then I would have to catch and send std current exception down the error channel anyway. Moving on, we have another implementation detail lambda, which simply queries the call to epoll CTL. It binds into it the epoll file descriptor, the actual file descriptor, and of course, a pointer to that events object we just synthesized 2 slides ago. Which brings us to actually implementing start. The first thing we try and do is we try and modify our interest set on the file descriptor. This is modally what we need to do, but epoll has a peculiarity. Epoll requires you to explicitly add the file descriptor the first time you interact with it, and so sometimes this call is going to fail with e no end. If it fails with anything other than e no end, we fail the whole operation because that's a critical error. Otherwise, we fall back and abstract away this peculiarity of epoll from our users by simply falling back to performing an equivalent epoll CTL add call. This is the reason why we encapsulated those in a lambda on the preceding slide, so I didn't have to stamp out a bunch of boilerplate. On the other hand, if neither of the operations fail, or if the only one we perform succeeds, we fall through to the bottom and we link ourselves into that intrusive linked list. We publish our presence through to the epoll context so it knows we're here, because now we fully set up execution. Now we're pending in the background. We've actually authored an asynchronous operation that has that property that it goes and sets up execution pending in the background. But operation states aren't useful on their own. They only come from connecting a sender and a receiver, and so of course we need to implement a corresponding sender. A sender is just a fully curried version of a function, and so it has curried into it the necessary arguments, and it has a constructor which populates them. Then, like we've seen before so many times, it has this sender concept which just opts it into being a sender for the purposes of the concepts machinery of std execution. But there is something interesting we've lost from the transition from synchronous functions to asynchronous ones. Synchronous functions advertise their return type. They advertise whether or not they are no accept. And we haven't seen that from asynchronous functions yet. And that's because that is the completion signature's nested type alias of a sender. It publishes a list of all the ways the represented asynchronous execution can complete. In our case, our asynchronous execution may complete by sending a value which is a mask indicating the forms of readiness obtained, or it may complete with an error which is represented via an exception putter. Which brings us to the purpose for which senders exist, being connected with receivers. Implementing connect with an appropriately constrained member function, stamping out an appropriate conditional no accept, and then finally returning the operation state. But not returning the operation state casually. No, we are very careful to return the operation state in a way that benefits from C++ 17 guaranteed RVO. Because operation states are immovable, we need to transmit them as an unmaterialized PR value out of our function back to our caller for them to materialize in the storage they have prepared for us. But we don't actually allow users to interact with this sender type. Instead, we provide a nice factory for them to obtain one, and so we stamp that out. Which actually brings us to the end of setting up work. If we just implemented this, user could go and grab senders and connect and start them. It's just that nothing would ever happen. For that, we need to implement run, which actually provides the concurrency and forward progress that we need. We see that the entire body of run is wrapped in a try-catch. This is because of the criticality of the receiver contract. If something goes wrong, we need to catch that exception and deal with it somehow. Also, because of the criticality of the receiver contract, we loop until each and every operation is done. We loop until the ops intrusive linked list is empty. Within that loop, we go and we allocate a buffer of 64 epoll events, and then we call epoll wait in an attempt to populate it. As I promised earlier, we pass -1 indicating that we want to wait for an infinite amount of time for this to happen. If an error occurs because we were interrupted, we just retry. Otherwise, we throw a system error, which is going to be caught by that catch block and then handled in a way we're going to see later. If, on the other hand, we actually dequeued some events, we need to go ahead and handle them. We need to visit each one using std for each. For each one, we go and we grab the closure pointer and we cast it to an operation state type. We remove it from the list of pending operations, and then we transmit the completion signal thereto. But note that the order of these operations is of critical importance. If we flip them over, we might send the completion signal to the operation state and tell it, hey, I'm done with you, only to find that the completion signal handling actually leads to the end of the operation state's lifetime because we said we were done with it. Then we would move on to the next line of code and try and unlink a dead object from an intrusive linked list and lead to undefined behavior. And so the order of these two operations is critical. Of course, things don't always go right. Sometimes our inner loop is going to end in error and throw and be caught, and so we need to take a look at how we realize that. Once again, we loop over all of the operations, we pop them off, and we finally send an error completion signal. But notice also that in both these cases, we're safe in the reentrant case. If any of the code that handles completion signals goes and tries to start a new operation, it will simply join the intrusive linked list. The intrusive linked list will no longer be empty. We will keep looping until each and every receiver contract has been satisfied. It's now possible to actually use this context usefully. You can go and you can grab a bunch of senders and start a bunch of work and then call run to try and drive all that work through to completion. But the person on the other side of that file descriptor isn't obligated to talk to you. They can just not send you any data ever. And if they do that, the file descriptor will never become readable. And you might think, okay, well then I can just move on with my program. But how are you going to do that? You can't let the lifetime of the operation state end because that operation hasn't completed, because the operation only completes when someone writes to the other side, which I already said they're never going to do. You are waiting indefinitely because we left something out of our implementation of this epoll context. We went and we modeled epoll, but we forgot about those stop requests that I talked about at some length earlier. But as we think about how we're going to actually implement stop request handling, we have a problem. We need to get the epoll file descriptor's attention so it can go and dispatch those stop requests, but the only way we have to do that is making a file descriptor readable. Fortunately, Linux gives us just such a capability in Eventfd. Under the covers, Eventfd is just a counter in the kernel, which you increment by writing to it and decrement by reading from it, and so we can write to an Eventfd and cause the epoll file descriptor to wake up. But first, we need to go and write an abstraction layer to give us an idea how this works. Of course, we have a constructor which performs the appropriate syscall with the appropriate checking in place, and then we get into what's truly interesting. The ability to write an unsigned 64-bit integer to the file descriptor by just writing its raw bytes. On the other side, the kernel is going to read those raw bytes and then add that integer to the file descriptor's associated counter. When the file descriptor's associated counter is non-zero, of course, it will show up as readable, and we're going to call read. At which point we're going to read the raw bytes of a 64-bit integer, which will give us the count the counter had before reading it, cleared it. Note that by reading it, we get the previous count and also clear its readability so it doesn't cause us to continually wake up over and over again. Revisiting our context, we're now going to make some targeted additions. We add an Eventfd wake up member, and then in our constructor, we need to associate it with our epoll file descriptor. Note that we only specify epoll in here. We no longer specify epoll one-shot. And that's because we want to get readability notifications from this file descriptor for the entire lifetime of our context. Moving on, revisiting our linked list, we need to add a second one just to keep track of those operations which are waiting for a stop signal. We don't want to have to visit every single operation to figure out which one it is that woke us up by writing to our Eventfd, so we simply duplicate our intrusive linked list to record operations waiting on a stop, and we add a mutex for good measure. Thereafter, we need to look at our type erasing layer, and we need to add an additional hook to it because it can now be in 2 intrusive linked lists rather than just 1. But we've also added a new completion signal, and so we need to add type erasure for it. So we add a new virtual member function. Which brings us to actually doing the meat of the work. Which brings us to modifying the operation state which actually performs type erasure. The first addition I make thereto is an invocable object which we're going to set up to be invoked when a stop request is transmitted. This embodies the action that is taken when we need to effectuate a stop request. We can see that we acquire a lock because a stop request can come from any thread. We add this operation state to the intrusive linked list of things waiting for a stop completion signal, and then we write a single value to the Eventfd. We increment its counter by 1, and we cause that epoll thread, if it's waiting, to wake up and dispatch this work. But simply having such an invocable does nothing to invoke it. For that, we need to go out to our stop token machinery and actually set up a stop callback, an object which represents an association between a stop token and an invocable which eagerly invokes that invocable whenever a stop request is received by that token. We go to our receiver and we extract the type of its environment. From its environment, we extract the type of its stop token, and then we use stop token stop callback for T to extract the type of the association between that stop token and our on-stop request invocable. Then we simply give ourselves an optional member thereof as a way to store that association. Moving on, we need to enrich the handling of the other completion signals with some additional functionality. We add this release private member function, which destroys the stop callback which associates us with stop requests. Then it looks to see if we had previously received a stop request, and if we had, it acquires the lock and backs that request out. It ensures that we will never receive that stop signal. We can see that the dispatch of value and error are enriched by adding an invocation of this at the beginning, which raises the question of why. Why are we doing this? Why is the stop callback in an optional? Why are we manually fiddling with its lifetime? And the reason for this is a problematic ordering. Imagine we didn't do this and we sent value or error through to the receiver, and then sometime later a stop is requested. That stop callback might be within its lifetime. It's going to wake up and it's going to sign us up to receive a stop completion signal. Then the epoll file descriptor wakes up, we receive the stop completion signal, and we sent multiple completion signals through to the receiver. As I said earlier, everything comes back to carefully ensuring that you cannot violate the receiver contract. Of course, we also added a new virtual member function, and so we need to stamp out the simple implementation thereof. Which brings us to enriching the logic that starts the operation with stop support. We need to go ahead and we need to create the stop callback to create the association between the stop token and our invocable. We do this by performing the same operations we previously performed in metaprogramming space. We go to the receiver and we get its environment. We go to the environment and we get its stop token, and we pass the stop token and instance of our invocable through to the constructor of the stop callback. But this raises the same sort of question. Why do we need manual lifetime management here? And the reason is another problematic ordering. Imagine someone connects a sender and receiver and obtains an instance of this operation state. They're under no obligation to ever start it. But then imagine after they do that, but before they start it, a stop is requested. The stop callback fires, it signs that operation state up to receive a stop signal. The epoll file descriptor wakes up and sends it, and once again, predictably, we have violated the receiver contract. The operation was never started, and so the receiver was guaranteed to receive 0 completion signals, but we sent 1 to it anyway. Turning our attention to our sender, we need to enrich its set of completion signatures and add the fact that it can complete with stopped. Then we need to go back to our run function. We need to go back to our run function, and as we're visiting events that we dequeue, we identify those that come from our Eventfd by the fact that their closure pointer is null. If this is the case, we set a Boolean flag and we keep looping. Which of course raises the question of why do we do this rather than dispatching those stop completion signals directly in line? And the reason for this is another problematic ordering. Imagine you did this. You detected that the Eventfd triggered the event and you dispatched all of the stop completion signals in line. Then of course you go back to visiting that buffer of events that you dequeued from epoll, only to find out that one of them is associated with a file descriptor that you just sent a stopped completion signal to. You of course send a value completion signal there too, and once again, sadly, predictably, you have violated the receiver contract. And so we need to use this strategy. But before we move on from here, note that once we set that flag, we also read from the Eventfd and throw the red value away. We do this to ensure that the Eventfd goes back to not being readable until someone else makes a stop request. At the bottom of our loop, when we detect that flag is set, we quickly acquire the lock and extract the entire list of operation states awaiting a stopped completion signal. Outside of this scope, we have a local copy, but we're no longer holding the lock, which means that we're not holding up other threads, and also that we don't run the risk of invoking user code while holding a lock, something that is incredibly important. Then we loop until we've drained the queue of all of the operation states awaiting stopped. We simply grab the front one and then pop it from the list. But if we just sent it a stopped completion signal, it would still be associated with the epoll file descriptor. We could still receive an event that appertained to it. We would then respond to that by sending a value completion signal to the receiver, which would, of course, lead to a violation of the receiver contract. And so we need to call epoll.ctl with epoll.ctl.del to break that association. If this fails, we throw an error, and then, of course, we're going to complete every operation with that error, so the fact that this can fail is not a problem. Of course, if this succeeds, it's now finally time to send that stop completion signal through, and so we do exactly that after erasing it from our global list of operation states. Which brings us back to that diagram we saw so long ago, the diagram of primitives that we really wish we had implemented, and it lets us check off the I/O multiplexer. Or does it? Is this really the interface we want to give to users? That you have to use raw file descriptors and raw bit masks to wait for a union of readability and writability? Or we'd rather give them an interface like this, one which abstracts away the raw file handle, one which gives them a separate view of readability and writability. And so we're going to go off and we're going to implement this as well. But unfortunately, I don't have time in the remainder of the session to do that, and so I'll ask for your questions and hope that you enjoy your coffee.
So typically there will be like one epoll object that contains a linked list of the different weight operations or objects that were created, and then whenever there's data on one of the file descriptors, then it will be sort of handled and removed out of the linked list.
Yeah, the question was about the overall shape, I think, if I'm understanding correctly, of the solution that we're presenting. And you're correct. You'll have a bunch of file descriptors, each of which has a single operation. Those operations are in a linked list, and they're also all inside of the epoll file descriptor. The only reason we really need the linked list is because when an error happens, we want to let them all know that we're done, and because we want to be able to find them when stop is requested. If it wasn't for the fact, actually, that we needed to drive the receiver contract through and we suspected that something might fail, we don't think we would need the global list, but we definitely absolutely need that so that when an error occurs, we can tell them all that they're never going to make forward progress ever again.
I have a question. When you actually finish the receiving, you need to stop the events from coming in because otherwise you can get another event and the receive is already finished.
The question was about the need to stop events once you send completion signal to the receiver, if I'm understanding correctly. The fact that we pass epoll one shot when we perform epoll CTL initially takes care of that. That tells the kernel that when you receive a readiness notification to this file descriptor, completely disable it and don't emit any other notifications about it until I get epoll CTL again. That was part of a couple of additions to epoll that were added after it was originally added, but not that recently, which permit it to be used kind of vaguely like the I/O multiplexers on other operating systems. I think the other one that everyone was really excited got added in addition to epoll one shot is, I think it's epoll exclusive, which allows you to do like multi-threaded waits on epoll and only get the notification on less than all of them. I don't use that here because this is, you have one thread and you surrender it to run.
So you are forced to call people on each receive to react.
Yeah, if you want to go back and start another operation, that operation is going to call epoll CTL again. You could perhaps make this code way more complicated to try and avoid that and optimize the number of syscalls, but in my use case, I just didn't think that it mattered.
So splitting every call with one shot epoll, doesn't it hurt performance? Like if you want to get the best performance from using epoll?
Yeah, the question was, does using epoll one shot hurt performance? I haven't actually looked at performance comparisons between not using one shot and using one shot. One shot is the most elegant way to map epoll onto this model. As I mentioned, you could conceive of a model where you dispatch the completion signal and then you use some extrinsic knowledge about what's happening to see if you already got started on a follow-up operation and avoid syscalls, avoid epoll one shot that way and avoid syscalls. I debated doing that, but it didn't seem worth it. My suspicion, which is not like a really good firm answer, I can't tell you, hey look, I've got a chart right here, is that the kernel maintainers probably wouldn't have added epoll one shot if they thought the performance was awful. And it seems to be pretty widely regarded that adding epoll one shot and epoll exclusive was a good idea. At least the people that I've read who complain the most about epoll caveat all the articles complaining about epoll by saying, oh, it has epoll one shot and epoll exclusive. No, it's fine. Yeah.
Do I have to destroy the receiver, like move it, or if I know that it can live, just use the same one?
In the current model, so this is actually an interesting question. The question is, do I have to move the receiver? The answer, I believe, if I'm remembering the specification correctly, is yes. So set value, set error, and set stop will not compile if you pass them an L value. You're obligated to pass them an R value. The question about maybe I can reuse them is an interesting one. The consensus among people who are experts in senders and receivers is that receivers are basically always a pointer. The most complicated receiver I've ever written is a counterexample to that. I mean, I really got them. It's a receiver, it's a pointer and an integer. So like that's my shining counterexample. And in fact, there's a paper making its way through the committee right now that would actually allow operation states to not store the receiver at all, right? Because most receivers not only contain a pointer, they only contain a pointer back to their parent operation state. Right, so you have all these pointers that go basically up one stack frame, wasting 8 bytes every time. We just saw the paper that would add that in Wroclaw, and Library Evolution voted that they wanted it, but we don't have wording for it. So yeah, the consensus opinion seems to be that receivers should not be where heavy data is stored. Moving them should be very cheap. We also have kind of a design approval to move forward with making it required that they can't throw when they're moved because they have to be so lightweight. And we estimate that the modal receiver just contains a pointer up one frame in the asynchronous stack, and then it can be completely elided through techniques that will hopefully make it in before C++ 26.
So can you describe a case when the ops linked list contains a different set of items than the stopping linked list?
The question was if I can describe a scenario where the two linked lists contain a different set of items. The stopped linked list will almost always be empty, right? It's only the operations that are waiting to be sent stopped. And the only reason it's there is because the Eventfd just tells the epoll file descriptor, hey, something happened, can you wake up and pay attention to it? When the epoll file descriptor wakes up, it's like if someone ran into your bedroom and woke you up and then ran away and didn't tell you what they wanted. You're like, wait, why am I awake right now? And so we need to have that list so that it knows that it came from the Eventfd because the closure is null, and then it goes off and it iterates all the things out of the stopped queue. And modally, that stopped queue will be basically one thing that's waiting for it. But in a really busy system, it could be more. But the master list of all the operations is going to contain every single operation that's outstanding. And if it doesn't, there's going to be a gratuitous amount of undefined behavior whenever those operations complete. So there's a two-part question. One is, what happens when you violate the receiver contract? And the other is, how can I detect I violated the receiver contract? So I'll answer the second one first. The spec says it's undefined behavior, which is not satisfying, right? What actually happens is that because this is all library code, the library code actually runs. And so the way that I detect this situation in my unit tests for all the code I've written, which is the code for this talk plus a lot of code, is in the unit tests for like each individual operation I'm writing, I'll have the receiver refer to a bunch of variables, one of which is a counter of the number of times it's been sent a completion signal. And at the end, the test fails if it's not zero. So I guess that answers both of your questions, right? It's undefined behavior in the spec. If you violate it, in practice, it just does whatever code it would do multiple times, and you can detect that by instrumenting it in your unit test to make sure that if you get multiple completion signals, you get a test failure that tells you that the code isn't well formed. The question is, if we don't have test coverage on these things, how can we check it at runtime? I mean, the way to check it at runtime, and I haven't looked into this, the question also was sanitizers. I mean, if you wanted to get a sanitizer hook, the quickest way would be to have all of your operation states contain all of your receivers, contain a flag indicating whether or not they've received a completion signal. If they transition that from false to true when they receive a completion signal, nothing happens. If they transition it from false to true when they receive a completion signal, if it's already true when they receive a completion signal, you call stood unreachable. And I think that my understanding is that UBSAN instruments that. You're going to get a UBSAN diagnostic if you call unreachable, as opposed to like in release mode, you might get SIGIL or something. I don't see, another hand.
Is there an intent to create such a library for
Yeah, so the question is if there's an intent to create a networking library kind of like this one for the standard library. With respect to the standard library, that is true. There was supposed to be a paper about that scene in Wroclaw in SG4, but the paper kind of missed, so we didn't see it. But there is interest in that space. If you want something more concrete than just, I'll wait till the standard gives it to me, I think that Dietmar Kuhl has a library that he's trying to get into Beeman. And also, Lewis Baker has the IOU ring execution context that I believe I referenced when I talked about IOU ring. I forget what library he actually has that in. It might be in NVIDIA StudExec and also and it's also in his personal library, which is called Squiz. He was just talking about how he got permission to open source that the other day. So it is in Squiz. Yeah, Inval's pointing out that if we do get networking, it definitely will not be on the 26 timeframe. Probably the 29 timeframe, but given the history that the committee has with networking, we might get it in like, I don't know, the 2040s. I think I've drained the hand queue, so everyone enjoy their coffee, and hopefully I'll see you back here for the next session.